Okay, now let's continue our discussion of the amniotes and talk about birds. So, birds have a lot of unique adaptations for flight as well as for other aspects of their ecology and behavior. And one of the most characteristic or hallmark features of birds is the presence of feathers and the presence of wings. There are other animals in the amniotes that have wings or maybe adaptations for gliding and for flight, but nobody but the birds have feathers. Now, their feathers are quite complex, and I'm showing you an image here of one kind of feather that shows some of the microstructure. So they're made up of a complex of shafts or rachis and barbs and barbules that together form this particular type of feather. And it's important to note that there is not just one kind of feather on the bodies of birds. There are a variety of different feathers that perform different functions. Some are specifically evolved for flight, some are for warmth and coverage. There are a number of different types of feathers. Now, we're not going to go into the gory details of the kinds of feathers. You'll learn that if you take ornithology, but it's important to note that there's not just one kind. And of course, the other unique feature among many of birds is the presence of wings on their forelimbs. Now, that said, not all birds, of course, fly with their wings. Some don't fly at all, and some swim rather than flying. But if you look carefully at those birds, what they're actually doing is literally flying through the water. So, penguins, for example, if you look carefully at the way that they move through the water, they're actually swimming through the water, or sorry, flying through the water. So these are diagrams that show some of the internal anatomy related to flight, and I'll talk a little bit more about this in a moment. But some important points to note is that their skeleton is specifically adapted for flight. For instance, most of their bones are hollow or pneumatic, and I'll show you some other pictures in just a moment. Their forelimb bones have been modified such that they really don't have much in the way of digits or fingers. Most of them have been lost. And feathers are attached to the skin that's attached to the forelimbs. They have a very large sternum it's large because they have huge muscles attached to the sternum, and those muscles are the ones that govern the wings and move them up and down. So hence they have huge breast muscles. They also have a furcula. That's basically their modified clavicle in the front. In fact, that's the wishbone that most people use, and also has muscular attachments that are related to flight. They also have adaptations for their feet too, but I'm going to show you that in another slide. This is a close-up, excuse me, down here of what the forelimb looks like for wings. So you can see that there's only 3 of the digits left. The other 2 are gone, and this one is actually reduced. So you get several different kinds or classes of wings among birds depending on what kind of flight they're engaging in. So these elliptical wings that you see here, which are characteristic of flycatchers and other birds, or other species, are for when you're flying in strategically complicated areas like forests. So they're having to maneuver quite quickly through many obstacles. These high aspect ratio wings, shown here on a swallow, are for rapid high flight, and so they're quite attenuate here. These dynamic soaring wings are not drawn to scale here. They're incredibly long and highly muscular, and they're used for long distance flight. So when you're flying very far away and need to basically glide to where you're going. By the way, I should back up. So this high aspect wings, these are also used by birds that are either eating on the fly or hovering where they eat. And lastly, these high lift wings for hawks and vultures and similar sorts of birds, those are for birds that are actually quite big. So they're broad as well as being long and allow them to afford great lift to get up off the ground and to carry a fairly heavy, bird up in the air. Other adaptations that birds have that are unique is that they have hind limbs that are adapted for walking, for swimming, and for perching, unlike other animals. So notice that their knees bend backwards from the direction that ours bend in. And they usually have 3 digits pointing forward on the hind limb and then 2 digits pointing backwards. And so they're often quite broad, their feet, and they're especially adapted either for walking in this case. If they're swimming, if they're waterfowl, they usually have webbed feet that allow them to paddle through the water very efficiently. And almost all birds that perch have interesting adaptations in their musculature and in their tendons that are related to their feet. And what happens is as they set their foot down onto a branch, their tendons automatically lock their feet. And so it locks them in place, which is a really handy adaptation so that they don't fall out of the trees when they're sleeping at night. Imagine how ridiculous that would look if the bird just fell out of the tree as it had been, snoozing away, snoring. That'd be no good. So their feet are adapted for actually locking into place so that they don't fall out. As you know, most birds, or all birds, have beaks. Now they vary in shapes and sizes depending on what it is that they're eating. All of them are keratinized, and they have short beaks with muscular jaws that allow them to, say, crush nuts. They have probing beaks for picking up plankton or shrimp in water. Of course, birds of prey have very sharp pointed beaks for ripping bits of meat off of their prey, and so on and so forth. And there's a lot of different adaptations among bird beaks depending on what they're eating. All birds lay eggs. They come in a variety of different shapes and sizes, but they all do lay eggs, and they all do lay them in nests. Those nests, as it happens, can be very distinctive, as well as their eggs, depending on where and how and they want to lay them. So sometimes they have very small nests with really small birds. They can make nests out of mud. They can make hanging nests. You name it. Birds are highly diverse in terms of the kinds of nests that they make for their offspring. And in some cases, there are some birds that are what we call brood parasites. So they actually lay eggs. They lay their eggs in other species' nests, and then they fly away. So they make the other species raise up their young. So coming back to their bones are exceptionally light, and they are feats of engineering. So they're light to assist in getting up off the ground and flying. If they had really heavy bones like we have, they'd probably never be able to get off the ground. And so to make them light, what they've done is they've gotten rid of most of the inside of the bone, and they have these struts that they've put in that'll allow the bones to be incredibly strong and at the same time very light. And they're referred to as pneumatic bones with a PN at the beginning of the word. Pneumatic bones. So related to this, birds are famous for their flight, but flight is an incredibly difficult thing to do. You need a lot of adaptations to your skeleton, to your muscles, to your nervous system in order to be able to accomplish this. And it's an incredibly high energy activity. So you also need modifications to your digestive system and even your reproductive system. You can imagine that if you were carrying an enormous number, more than a couple of eggs in your reproductive system, it might be really difficult to fly if you had all of them gestating inside you. So hence, they don't usually really carry those eggs around for very long. They lay them in nests. So let me give you let me show you a slow motion video of what flight looks like. Most people think flight is accomplished by merely flapping wings up and down, but it's actually much more complicated than that. Now, the way that the wings are moved depends on the kind of flight that they're accomplishing. But just to give you an example of what this might look like, take a look at this pigeon in slow motion. So you can see that what's happening is it's moving its wings forward and then very far back. They're pretty much touching back behind its back. It's difficult for most of us. I'm going to play that again. It's difficult for most of us to even move our arms all the way back and touch our hands behind our backs, although maybe you could do it as a kid, but it's really hard to do it now. And so what they're actually doing, if you look carefully, is they're not actually flapping their wings up and down. In fact, what they're doing is they're making a figure 8. If you look at the leading edge of the wing, one more time, take a look at it. They're in fact doing a figure 8 with their wings. that takes an enormous amount of musculature in their pectoralis muscles. It's their pectoralis muscles that are moving the wings down, and it's their supracoracoideus muscles that are moving their wings backwards. And they have extremely well-developed pectoralis and supracoracoideus muscles to accomplish flight. Okay. Moving on. So let's talk a little bit about the evolution of flight. Most people are really curious about how birds managed to evolve feathers and wings and where they came from. Well, there's a lot of evidence in fossil forms, and we're only going to cover a few of these fossils because we don't have time to do more. But this is the classic example of Archaeopteryx. So this is one of the first ancestral forms of birds in the fossil record, and I'm going to show you some more in just a moment. But what's really interesting about and important about this fossil is that it shows very distinct outlines of feathers in the rock. And for those paleontologists that have examined these samples very closely, it's clear that most of the bone elements of this species were very reptilian. So it had many aspects of its skeleton that were in fact reptilian in nature rather than being bird-like in nature, but it clearly had the feathers in the skull of a bird. So this particular individual was about the size of a crow. It had a skull, again, like modern birds, although it had teeth in sockets like dinosaurs have rather than, what birds have, which is nothing. The skeleton looks rather reptilian. It had a long bony tail, which you can see right here, rather than the short tail that most birds have. It had clawed fingers, which you can see here very clearly. And it had abdominal ribs down here, which birds don't have. Normally they only have thoracic ribs. So here you go. Here are the thoracic ribs of birds. Most birds, by the way, have a very long neck compared to most reptiles. They only have a really short tail. And you may or may not be aware, but most of their skeleton is pretty rigid. There's not much flexibility in the skeleton, with the exception of the appendages. The wings and the legs have quite a bit of flexibility, and really only the cervical vertebrae of the neck have much flexibility. Sometimes in the neck, most of the rest of the skeleton is pretty rigid. So as an example, here's a classic lizard, and you can see that there's thoracic ribs and abdominal ribs that go all the way down, whereas birds only have these thoracic ribs up here. And that Archaeopteryx had abdominal ribs as well. Okay, clearly had unmistakable feathers, which I mentioned already. To explain the name, Archaeopteryx lithographica means ancient wing inscribed in stone. So a well-made Latin name. All right, let's talk a little bit more about the evolution of flight. So this is a phylogeny from your book showing the Saurischia, and here's the modern aves and then the Neornithes. So let's start at the bottom. So what are the changes that have occurred throughout amniotes from former dinosaurs leading up to the modern birds? So one of the first adaptations was the Saurischian pelvis. So if you look at the pelvis of dinosaurs, they were very interesting. It's rotated down differently from ours. So here's the ilium, here's the ischium. The ischium are your butt bones, if you will. So when you sit down or when you sit in someone's lap and you feel those bony protuberances, yeah, that's the ischium. And your pubis is, of course, in the front. But notice that these elements come together for the pelvic girdle, but they're sort of rotated down. So ours is kind of rotated up a little bit more than this is. But it looks close to what modern birds have. Now, sorry, actually not in that one, the next one. So let me back up for a second. By the way, these guys, many of them, so we're talking about a development from a quadrupedal animal to a bipedal. So this is an example of one that's a bit more bipedal, but you're going to find that it gets rotated up with animals that are much more normally bipedal. So, as you work your way up the phylogeny to the basal theropods, these are animals that are now bipedal. They have hollow pneumatic bones like modern birds, and they have a tridactyl foot. Now, sometimes they have 2 digits that are backwards, but usually it's but for the ones at this point, it's 1 digit back and 3 forwards, like you see here with emus. Next, we have filamentous protofeathers. So these look. So these are the precursors to modern feathers. These don't have all the same elements within each of the modern feathers that we see today, but I wasn't concerned about you knowing too much about the gory details of the makeup of feathers. They have lunate wrist bones and a furcula. So the bones in our wrist, if you look at them, in us, they just kind of look, well, here, let me show you a picture. So they're called lunate because they look like a half moon. So there's a little curve in there, and that allows each of these bones to actually fit together and articulate. So birds have lunate wrist bones, and you see the development of these right after the Sinosauropteryx, so right here with the dromaeosaurs. As for the furcula, I mentioned that earlier. So that's a modified clavicle, and here you know of it as the wishbone. But there are some important attachments. So here's our clavicle, and here's a bird's clavicle. So these are modifications for flight and have muscles attached to them that help them and assist them with flight. Next are symmetrical and veined feathers. So instead of having those protofeathers, now you're getting feathers that are veined and they're symmetrical. That's followed by asymmetrical flight feathers. So in order to accomplish flight, you actually need a different kind of feather. So you actually want them to be asymmetrical. And that allows you to get greater lift off the ground and to glide. So in order for flight to work, so let's talk about that, you need wings for lift. So you need to be able to get off the ground, and then you need propulsion. And then once you get in the ground, off the ground, you need to be able to keep going. Okay? So these are some images of a duck that's actually moving its wings in order to fly through the air. So what else do you need in order for flight to work? Well, you need light but hollow bones and a rigid frame so that it can take, landing and taking off. There's an awful lot of thrust that has to go on when you get off the ground. And then as you land, you need to be able to, withstand the impact of that. So I showed you some images earlier of the bones of birds. They also need a highly efficient respiratory system. So birds have a really unique respiratory system. Most of what are referred to as lungs, and even in this picture, are really referred to by others as paralungs or parasacs, parabronchi. So what they have are a number of different sacs, and instead of, with us, we breathe in and we breathe out. We breathe in and we breathe out. And when we breathe in, when we inspire, you're taking in air, some of which is oxygen. And most people seem to think that when we breathe out, what we're breathing out is carbon dioxide, because that's what you get told from elementary school on. We breathe oxygen in and carbon dioxide out. And plants, of course, are noted as, taking in carbon dioxide and giving off oxygen. Well, with respect to our inspiration and expiration or exhalation, so in fact, when we breathe out, we're not just breathing out carbon dioxide. In fact, most of that is the very air that we breathe in. Most of it is oxygen. Okay, or it's a similar amount of oxygen as we took in. So some of that oxygen does get extracted into our lungs and it's used by our body, but not all of it gets extracted. It's actually not a very efficient system compared to what birds have. Birds are incredibly high energy, their muscles are working constantly, and in order to make sure that those muscles continue to work, they need high levels of oxygen to power them, among other things. So in order to be able to accomplish that, they have a really interesting set. It's a set of one-way lungs, in effect. So we breathe in and we breathe out. They, when they inspire through the trachea, their air goes first to the back to a set of posterior sacs, seen here. So that's when they inhale. When they exhale, this air that they just inhaled is going to go into the lung with the parabronchi, and this is where oxygen is going to get extracted. When they breathe in a second time, the air in the parabronchi are going to go into the anterior air sacs. And when they exhale again, that air is going to get sent back out. So to follow through, they inspire here to the posterior sacs. They exhale, it goes in the parabronchi. They inhale, the air then goes into the anterior sacs. They exhale, and then all that air goes out. And so each time they inhale, there's air going back here. So they're constantly inhaling, exhaling, inhaling, exhaling. So when this air gets pushed into the parabronchi, they're in the next inspiration, there's more air going back here. So there's always air constantly flowing through their lungs and having oxygen extracted out of them. By the way, I think I misspoke. So the air is getting extracted into the body through each of the pairs of lung sacs, so not in the parabronchi. So let me show you some videos that hopefully will explain that in a bit more detail.
The structure of avian lungs enables more oxygen to be extracted from the air, enabling birds to fly at altitudes where mammals would succumb to hypoxia. The lungs are made up of the trachea, through which air enters the respiratory system. Air sacs, positioned both at the anterior and posterior of the gas exchange surface, act like bellows, keeping a continuous flow of air through the lungs. They allow air to be moved through the respiration system without having to expel air from the body. The lung is made up of parabronchi, which act as the gas exchange surface.
Oops, sorry, I misspoke. It is the lung after all.
The movement of air in avian lungs can be broken down into 4 parts. During inhalation 1, air moves from outside the body through the trachea and into the posterior air sacs. In exhalation 1, the air then flows from the posterior air sacs into the parabronchi of the lungs, where gas exchange takes place. From the lungs, the deoxygenated air then flows into the anterior air sacs, where it is held until exhalation 2, where the air is expelled from the body through the trachea. This system therefore creates a unidirectional flow of air across the lung, which means that all air that comes into contact with the gas exchange surface is oxygenated, making the lungs more efficient. Another adaptation of the avian respiratory system which increases efficiency is the cross-current blood flow across the air capillaries in the parabronchi of the lungs. The blood capillaries are arranged across the air capillaries where gas exchange occurs. This means the rate of diffusion of oxygen into the blood is increased due to the sustained high concentration gradient.
All right, let me show you another one just to reinforce those ideas. Don't worry, there's no sound you're missing here. All right, so hopefully those videos, hang on. So hopefully those videos out of what's happening with the respiratory system of birds. Other adaptations that birds need is a rapid, efficient digestive system. So they need to be able to eat small amounts of food and extract energy from it efficiently. They can't just be sitting around, consuming an entire antelope because they can't take off from flight if they're busy digesting food. So as I mentioned when we talked about the archosaurs, they have a crop and a gizzard to facilitate that breakdown. And particularly the gizzard is full of muscular structures and sometimes things inside to help do the physical breakdown of the food. Now, in the case of some birds actually eat nothing but nectar, like hummingbirds, so it's high energy food, and they don't need to drink a lot of it. They continuously drink, and most birds are famous for the fact that they kind of continually eat throughout the day, again, because they can only eat small amounts, and yet at the same time, they need a lot of energy. So that whole cliche about, oh, someone's got the appetite of a bird, well, that's really saying something, because birds are known to eat about 4 times their body weight. So that's a sizable person that you're talking about if you say they have an appetite of a bird. So don't think for a second that means they don't eat much. So some birds do some really interesting things in their digestion. Most birds eat food and then extract it or eliminate the waste, as do most of us. But their owls are quite famous for eating, let's say, rodent items, and they partially digest it in the forepart of their gut. But then things like bones and fur get spit up as these pellets that probably all of us, tore apart in elementary school. And by the way, be really careful when you do that. If you get those from a company, it's probably okay. It's been sterilized. But if you pick those up in the woods, you can get some nasty infections from picking up. There's lots of germs and stuff associated with those owl pellets, so be careful. Anyway, they have a rapid and efficient digestive system. They have a high pressure circulatory system that, again, is feeding their muscles and the rest of their body the nutrients that they need, the oxygen that they need. And you may or may not know it, but man, birds have a really high pulse rate. So turkeys are like the slugs, if you will, of the bird world. They have a 93 beats per minute. Most chickens are clocked at having about 250 beats per minute. And then things like chickadees have anywhere from 500 to 1,000 beats per minute, and hummingbirds are like off the chart. Their hearts are beating like crazy, and they're one of the few birds that can actually hover, while they're eating. And so it takes an enormous amount of energy, and so a high pressure circulatory system to be able to accomplish that. I'm going to talk more about this in class. So birds have an incredibly highly tuned nervous system. They have incredible eyesight. Not the greatest sense of smell, with a few exceptions. Most of them don't smell so well. But they do have incredible hearing as well. And that relates to other adaptations regarding courtship, territory defense, and other things. And so, of course, they're famous for their bird calls. But they are incredibly intelligent organisms that have really highly developed nervous systems and sensory systems. And I'm going to show you some videos in class. I'm going to cut it off for here, but I'll show you some other ones in class. So that's all I'm going to tell you about birds. We will finish up with the next and final chapter, chapter 20, in the next video.